Chapter 7 Overview. Chapter 7 deals with three kinds of linear mappings called operators going from V into itself, where VK is a vector space having a fixed positive definite scalar product. We look at symmetric operators, Hermitian operators, and unitary operators. Of course, you're already familiar with symmetric matrices. A matrix is symmetric when it equals its transpose. But the other two you were not so familiar with. So it starts off with the treatment of symmetric linear operators. So we start with a linear mapping, A, going from V into V. Then we have this lemma, 1.1, which I have stressed 2 or 3 times in my notes, that tells us that there exists a unique operator B with the inner product of AV with W equal to the inner product of V with BW for all V and W in V. This unique operator is the transpose of the operator A. So this is the definition of the transpose of a linear mapping. So we have the scalar product of AV with W always equal to the scalar product of V with the transpose of AW and vice versa. Now, A is symmetric when transpose of A is equal to A. That is, when this unique operator we're calling B, when it's equal to A, then A is symmetric. So, if A is symmetric, we find that the scalar product of AV with W is always equal to the scalar product of V with AW, and vice versa. And our most important example is Kn. So when our vector space is Kn, we have the usual dot product of x dot y, which is defined as transpose x times y, where x and y are elements of Kn thought of as column vectors. So transpose x is a row vector, y is a column vector, and you're simply taking the normal dot product of the row x with the column y. So now when you input that into the scalar product, you get the scalar product of AX with Y by definition now equal to the transpose of AX times Y, which is, you've already seen before, is equal to transpose X transpose A times Y, which equals X scalar product with transpose AY. So here, transpose A now means the transpose of the matrix, which you know is just interchanging the rows and the columns. Okay, theorem 1.2. Again, when we're given a vector space V over a scalar field K with a non-degenerate scalar product, we have these 4 properties that you're proving for homework: that the transpose of the sum of AB is the sum of the transpose of A plus the transpose of B, etc., etc., etc. So you have those 4 properties that are very important and very easy to prove. Next, in Chapter 7, Section 2, we talk about Hermitian operators, but we first start out with a vector space V over the scalar field of complex numbers with a fixed positive definite Hermitian product. Now, back on exam 3, you proved that the vector space V is isomorphic to V star, which is the dual space. Remember, V star is the set of all linear maps going from V into the scalar field K. Alright, so since V is isomorphic to the dual space V star, given any functional L in V star, there must exist a unique element W prime in V with L of V equal to the scalar product of V with W prime for all vectors V in V. Again, that's theorem 2.1 on page 184. Next, on page 185, given our operator A, there will always exist a unique operator, A star, going from V to V, with the scalar product of AV with W equal the scalar product of V with A star W for all V, W, and V. A star, you could call it A asterisk, is called the adjoint of A. The adjoint of A. Again, our classic example is when our vector space is Cn, the vector space of all ordered n tuples with complex entries, complex coordinates, and the dot product on Cn, the usual dot product on Cn, x dot y, is where you take the row vector x times the conjugate of y. So that's row x dot product with the conjugate of y, the complex conjugate. So when you place this into the scalar product with ax with y, work it out there, you'll notice you eventually wind up with a star equal to the transpose of a conjugate, which is also equal to the conjugate of a transpose. So you see here the transpose and the conjugate are interchangeable. Doesn't matter which one you do first. Transpose of the conjugate is equal to the conjugate of the transpose. That equivalence is very important. That's for matrices with complex entries. Now, an operator, A, is called Hermitian, or another word for it is self-adjoint, when A star equals A. Again, of course, that means that the scalar product of AV with W equals the scalar product of V with AW for all V, W, and V. Again, that's the definition of Hermitian. Okay. So when our vector space is Cn, a matrix A is Hermitian if transpose conjugate A is equal to A, which is the same as conjugate of a transpose of A. This implies a very important equivalent, that A is Hermitian if its transpose equals its conjugate. This last implication is probably the easiest one to work with and the most commonly applied. A matrix is Hermitian when its transpose equals its conjugate. And then you had the homework for theorem 2.3 on page 186, which is the same as the other theorem for the transpose of operators with the star, the dual space operator. Then finally, we have a couple of theorems to end 7.2 on page 187. Theorem 2.4, very important. Whenever the scalar product of AV with V, the same vector V, is equal to 0, if that's true for all vectors V in V, then A must be the zero operator. The zero operator, that's kind of a non-degenerate type property. And then a consequence of that, theorem 2.5, very important. A is Hermitian if and only if the scalar product of AV with V is real for all vectors V in V. Now this theorem 2.5 has important implications in chapter 8 when we look at the eigenvalues for both symmetric and Hermitian matrices. Turns out that their eigenvalues are always going to be real, not complex. Third, 7.3, unitary operators, which more commonly referred to in the entry-level class as orthogonal. First, we have the real case, and then we apply it to the complex case. First, the real case. Given the vector space V over the scalar field of real numbers with a positive definite scalar product, and given our operator A, we say that A is real unitary, or simply orthogonal, if the scalar product of AV with AW equals scalar product of V with W for all VW. We say that A preserves the scalar product. And an implication of that definition is theorem 3.1 on page 189. We have three properties that are equivalent now for unitary operators. They are: 1, A is unitary; 2, the norm of AV equals the norm of V; and 3, if the norm of V is 1, then the norm of AV is also 1. So that third one says that a unitary operator maps, unit vectors to unit vectors. And also, it's quite obvious that a unitary map preserves perpendicularity. That is, the scalar product of AV with AW equal the scalar product of VW equals 0, meaning V is perpendicular to W if and only if AV is perpendicular to AW. Okay. Theorem 3.2. Given V over R with a positive definite scalar product and operator A, turns out that A is unitary or orthogonal if and only if transpose A times A equals the identity. What's that? That's definition of an inverse. So that means that A is unitary if and only if the inverse of A equals the transpose of A. Now, implied in this theorem is the fact that whenever a matrix or an operator is unitary, the inverse always exists. They'll always have an inverse, and their inverse equals the transpose in the real case. So that's what I'm saying on the next line there. When V is equal to Rn, A is unitary, orthogonal, if the inverse of A equals the transpose of A. The complex case, when we have V over the scalar field of complex numbers, positive definite Hermitian product, the definition of unitary is the same. A is complex unitary, means the same thing as the real case. The scalar product of AV/AW equals the scalar product of V with W. And we have the corresponding theorem for the complex case. A is unitary if and only if A star A equals the identity, meaning the inverse of A is equal to the adjoint of A star. So when V equals Cn, we note that A is unitary if and only if its inverse is equal to its adjoint. Now, for matrices, the adjoint of A, or A star, is equal to the transpose of the conjugate of A, which of course is the same as the conjugate of the transpose of A. So if you do one more conjugation on both sides of that equation, the implication here is A is unitary if and only if its transpose is equal to the conjugate of the inverse. And it's also true that the conjugate of the inverse is equal to the inverse of the conjugate. Now, I will make one more comment. I didn't write down theorem 3.4 at the end of section 7.3 that talks about orthonormal bases. I'll say this. In the case of matrices, a matrix is symmetric and/or Hermitian when the columns of the matrix form an orthonormal set of vectors. That is, a matrix, a real matrix is symmetric, a complex matrix is Hermitian whenever its columns form an orthonormal set. That is, the columns of the matrix are mutually perpendicular and have unit length norm 1. That concludes the overview of Chapter 7.